Before I start telling you about the subjects I want to cover today, just let me draw your attention to what's written on the whiteboard. You should try those homework problems, and I've written down the corresponding numbers in the 9th edition. Okay, at the end of the last lecture, I started to talk about conjugated systems, and I pointed out that you can have double bonds in a chain, or indeed in a ring, arranged in various ways. You can have an isolated double bond. Ethylene is such an example. Or you could have double and single bonds alternating down the chains. You have double, single, and so on. Those are conjugated double bonds. Or you could have double bonds between contiguous carbons. In other words, a carbon double bonded to a carbon, and that carbon double bonded to another one. And those things are called cumulines. And the very simplest one is called allene. That's what I ended up with in the last lecture. And I also told you how to name some of these things. And I do believe that I also gave you some examples in which, instead of a double bond, you have a some idiot has programmed this to switch off as soon as I start. It's my fault, of course. I should realize that it's around. I should have taken a practice before, but in a few minutes that thing will cool down and then I can switch it on again. Okay. I also gave you examples in which instead of double bonds you have triple bonds, and you remember that those things are called ene-ines. It doesn't matter how many ines there are and how many enes there are or where they are called ene-ines. But where the complication is in how you number them. If you have double and triple bonds in a chain, you have to number from one end of the chain to the other. And what you do is you write down two pictures of the compound, and you number first from the left, and then you, in the other picture, you number from the right. And the order in which the one that you choose depends on which picture gives you the smaller number at the first multiply bonded carbon. And once you've identified that, which of course is very easy, you can then write down the name of the compound. But there is a little complication, because let's see which example I actually gave you. I've got right time. Oh, that's funny. Just hang on a moment while I find the example that I gave you. Yeah, okay. I didn't give a particular example. If there's a choice, supposing if you number from the left, the first multiply bonded carbon, that is to say our number triple bonded has the number X, and if you number from the right, the first multiply bonded carbon has also the number X, then the one that you use is the one that gives preference to the double bond. Okay, that's what I told you last time. What I want to do now is to talk quite a bit about a particular conjugated compound. It's a very simple one. It is this one, which is 1,2,3,1,3-butadiene. Now, 1,3-butadiene is a very simple example of a conjugated system. And it turns out that 1,3-butadiene can exist in several conformations. Now, you should remember from Chem 261 And there's
Right, I can speak for 5 hours now without it switching off. I'm sure you're happy to hear that. You should remember from 261 that the word confirmation means the arrangements in space of the atoms that can be attained or reached by rotation about single bonds. And in the case of butadiene, 1,3-butadiene, I can have that arrangement. Now these two are given different names. This is called the S-cis, and this is called the S-trans. And the S just stands for single bond. And the word cis is on the same side. And you can see that the one that I've labeled S-cis has the terminal CH2s pointing on the same side. And the one that I've labeled S-trans has them pointing on opposite sides. So the naming is very, very easy. Now, as you also know, you could easily guess that this one, the S-cis, is less stable than the S-trans. And the reason for that, if I draw the picture again, these two babies come close together and bump into one another, or certainly close enough to repel one another. So there are two conformations. That repulsion is not prohibitively strong, but it exists. It makes the S-trans more stable than the S-cis. The other thing you need to know about butadiene, as I've said already a few times, is it represents a conjugated system, and from things that I've told you already, that should mean to you that it is more stable than if it weren't conjugated, and I'll explain in a moment in more detail what I mean by that. The other thing it should mean to you is that the electron density in overlapping p orbitals is somehow spread over the whole system, so that this is not a real double bond, this is not a real single bond, and that is not a real double bond. Because in a real double bond, the p orbital here overlaps the p orbital there with nothing else. And here in a single bond, there is, if this were a true single bond, the p orbital here and the p orbital there would not be allowed to overlap with one another. But you will see when I draw up the molecular orbital picture how, in fact, the electron density is smeared over the whole carbon framework. Okay, so let's see what the molecular orbital picture is. Now, what I'm going to do is I'm going to consider only the p orbitals. On this carbon, there's a p orbital. This carbon is a p orbital. That one's a p orbital. That one's got a p orbital. And I'm going to mix these orbitals in various ways. And there's a general rule which comes out of quantum mechanics that when you mix orbitals, you can't lose any. So if you mix 4 orbitals, you have to end up with 4 new orbitals. You can't end up with one big one or 2 fairly big ones. If you start with 4, you end up with 4. Now, as you know, these orbitals, these p orbitals, they can be given an arithmetical sign, which means something in the quantum mechanical treatment. What it does not mean is charge. So I'm going to draw 4 orbitals. Let's do it here. I'm going to draw p orbital with plus and minus. I'm going to draw p orbital with plus and minus. I'm going to draw p orbital with plus and minus. And a p orbital with a plus and a minus. And now I'm going to draw another one. This is now, I'm going to call it pi 1. I'm now going to draw another pluses and minuses do not mean charges. Plus, 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 minus, 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 minus. This I'm going to call I2. Now I'm going to draw yet another one. Plus, minus, plus, minus, minus, plus, minus, plus. That's going to be I3. And last of all, plus, minus, plus, minus, plus, minus, plus, minus, and that is I4. Now, I draw this one here first, right in the middle, so everybody can see it clearly. When the signs are the same, there's a nice overlap, which means there is electron density between this carbon and that one, between this one and that one, this one and that one. And if we've got electron density between two atoms, that means there's a bond. In this one, there's clearly a bond here, atoms 1 and 2, and clearly a bond here because the signs of the nodes are the same. But in fact, there is a node here. So there is very little electron density here from these pi systems. In this one, that's funny. What have I got? Let me just got it out. Yeah. No,
Plus, minus, minus, plus.
Okay, so in pi 3, there's good overlap for the central bond, so it's looking like a double bond, and lousy overlap here, and lousy overlap there, and in this one, it's poor overlap there, poor overlap there, poor overlap there. So you can see that much of the bonding comes from pi 1, and then some of it comes from pi 2, and those contribute less. And these orbitals, these orbitals have different energies. So let's just write it down. Pi 1, pi 2, pi 3, and pi 4. Now, every orbital, there's a rule, a quantum mechanical rule, which says any orbital, and we're dealing with molecular orbitals, can have only 2 electrons in it. So let's put in, you've got 4 electrons to begin with, because we've got 4 p orbitals, each with 1 electron. We put 2 in there, and we put 2 in there, and these are empty. So that is the orbital picture. These are the bonding orbitals. Those are the bonding orbitals. And these two are called the anti-bonding orbitals. This one is given a special name. It's called the HOMO, which means the highest occupied molecular orbital. Highest occupied molecular orbital. This one, pi 3, is given also a name which is called the LUMO. And if you think think about it in a moment, you probably guess that that means the lowest unoccupied molecular orbital. Because these orbitals increase in energy. The highest one that's occupied we call the HOMO, the highest occupied molecular orbital. And the lowest energy one that is unoccupied we call the lowest unoccupied molecular orbital, or the LUMO. And there's a reason for identifying this is highest occupied and lowest unoccupied. Because if you shine light on this stuff, of the appropriate wavelength, it will absorb some of the radiant energy. And when it absorbs some of the radiant energy, one of the things that can happen is that an electron can be boosted from the highest occupied orbital to, for example, the lowest unoccupied orbital. And obviously, if the difference between here and here is very small, you don't need very much energy to do that. Whereas if it's very big, you need a lot of energy to do that. So this picture, which I've given you in a very, very simplified form, tells you certain things. One of the things that it tells you, because of this, is that this central bond is somewhat like an ordinary double bond of ethylene, because it's got the orbital overlapping. And so this central bond has a different bond length from an ordinary single bond. Yet in the pictures that we write, when I write, let's say, well, this picture, say, I draw that as though it were a single bond, but it isn't a single bond. Now, conjugated dienes, such as, yes, you've got a question.
So you said you shine light on this,
Yes.
But if they're going from a high energy or a lower.
No. Even though I call this a low energy, you must realize that that word low is associated with the rest of the name. It's the lowest unoccupied. Okay? Imagine a tall skyscraper, 50 floors. And business is bad, they've only rented out floors 1 to 25. So the lowest unoccupied floor is floor 26. But it's still higher than the other floors, even though you put the lowest unoccupied floor. You got it? Right. Conjugated dienes are thermodynamically more stable than isomeric compounds that don't have double bonds in them. Now remember, I told you before, without full explanation, you can't at this stage explain these things fully and then get into heavy-duty maths. I told you that conjugated systems, or systems for which you can write resonance structures, are more stable than corresponding systems for which you can't write resonance structures. And you will see that this is just a molecular orbital picture of a situation for which you can write resonance structures. So conjugated dienes are more stable than corresponding non-conjugated dienes. And that's very easy to show by a very simple experiment, which is easier to understand than all this theoretical stuff. Now, some of you may be wondering, why did he line them all up with pluses on the other, and the next one 2 pluses and 2 minuses, and so forth and so on? I haven't really given you a reason. Those are the rules for doing this. If you want the rules, if you want some deep insight, you better become very good at mathematics, because it all comes from a mathematical treatment. Now, I want to show you an experiment to prove to you that if I've got a couple of conjugated double bonds, that system is more stable than if I've got another compound with 2 double bonds that are isolated from one another, so they're not conjugated. If I can do an experiment to prove that, that immediately tells you when you've got conjugated double bonds, in other words, when you can draw these molecular orbital pictures that overlap over the whole system of conjugated double bonds, or when you can write resonance structures, because I can write resonance structures of butadiene, I will do that shortly. When you can do that, it becomes more stable. So far, I've just told you that a few times. But you don't have to believe me. Well, you should believe everything I tell you, but you don't have to take my word for it. There's a simple experiment you can do. It's very, very simple. Supposing you take a compound and you burn it. What you're doing is you're combining it with oxygen. And what is coming out is carbon dioxide and water and energy in the form of light and heat. Now, if you take two compounds and you burn both of them to carbon dioxide and water, the final products in both cases are the same, carbon dioxide and water. And supposing the energy level of those products is some value, let's say you could represent it by the surface of this bench. And supposing the starting materials have a higher energy level. So when I convert the high energy content compounds into carbon dioxide and water and heat, this is the energy that comes out. If I have another compound that's even higher in energy, then the amount of energy that comes out will be even bigger. So what we're going to do is we're going to take a few compounds and we're going to burn them. And every one of them is going to give us carbon dioxide and water plus some energy. And we're going to take one compound that's got a conjugated double bond and another that has no conjugated double bonds but has double bonds. We're going to measure the relative amount of energy that comes out. But what I told you, that is to say that conjugated systems are more stable, they're lower in energy. So the amount of energy you get out, the amount of heat you get out is going to be less. That's very easy to do. The experiment that you do is this one. We will take 2 moles of that. Actually, I'm not going to burn it. I'm going to do another reaction. What I'm going to do is I'm going to hydrogenate that stuff. You can do it with burning as well. I'm going to hydrogenate this. So this is at a certain energy level. And I'm going to hydrogenate it. That's hydrogen and catalyst. And I'm going to get 2 moles of butane. And then I'm going to hydrogenate butadiene, and again I'm going to get out butane. Now the energy that I get out from this one is bigger than the energy I get out from that one. But in both cases I've taken 2 double bonds and saturated them. So I've gone to the same place. And in the case of the conjugated one, if you actually do the experiment, you get out a sizable amount less than the non-conjugated one. So we have to conclude that the conjugated starting material is at a lower energy than the non-conjugated starting material. Because the final products are the same, they're both butane. I have a conjugated diene, I hydrogenate it to butane. So I'm saturating 2 double bonds. That happens to be an exothermic reaction in butane. And I measure the amount of heat that you get out. Then in another experiment, I take 2 molecules of a non-conjugated double bond, hydrogenate them, again to butane, measure the amount of heat that's given out. And so experiments like that prove that conjugated systems are more stable. Now, there's another feature about conjugated systems. You could do another experiment, not only linear compounds, you could also do the thing, the experiment with this. See, I can start with two dynes. One is conjugated, and the other one is not conjugated. But in both cases, I'm saturating two double bonds. You would get out less heat from this than from this base, because this one does not have conjugated double bonds. So that's the rule. If the things are conjugated, it's more stable. Now, a moment ago, when I drew up the lowest occupied molecular orbital, then the highest occupied molecular orbital, then the lowest unoccupied molecular orbital, and the remaining unoccupied molecular orbital, when I drew those up, I said that one of the interpretations, or one of the reasons for knowing something about the fact that the orbitals are at different energy levels, and you fill them up from the bottom, putting two into each orbital. One of the reasons for that is that you can then understand what happens when the compound absorbs light. Because one of the things that can happen when a compound absorbs light is that the energy is used to boost an electron from the highest occupied orbital to the lowest unoccupied orbital. And I pointed out that if the energy gap between those two orbitals is big, then you need a lot of energy, and if it's small, you need much less energy. And it turns out that conjugated alkenes absorb in the UV and visible region of the spectrum. You know that ordinary light consists of something called electromagnetic radiation. You know that it has strange properties discussed by people who study quantum mechanics. Some of its properties are best understood as though it were a wave, and some of its properties are best understood as though it were a particle, and it doesn't have the same properties at the same time. All peculiar, very strange things resulting from quantum mechanics. But there are a few things that you know. You know that some electromagnetic radiation is harmful to you. Go out into the UV and the sun, or shine low X-rays on your skin, you'll be in trouble soon. And some of the radiation is not harmful to you. And you probably know that the differences between these various types of radiation are the wavelength or the frequency. Now, what we need to know, just a little bit about this, so that you can understand why carrots are red. Carrots are red, conjugated double bonds, and they absorb at a certain region, and the net result is that what's left is perceived by the eye as red.
Yeah, the orange. Orange.
Many years ago in England, there was a fellow who was one of these health food nutcases. He persuaded himself that he should drink large quantities of carrot juice. And he became quite hot. And he persisted in drinking large quantities of carrot juice, even though his doctor and his wife warned him this was not a good idea, but he was obstinate. Okay, there are a few things we need to know about electromagnetic radiation. One of them is that the energy frequency in hertz. So hertz just means cycles per second. There's another equation, E equals hc over lambda. I'm going to write that lambda right there. those are a couple of features of electromagnetic radiation. These equations apply to visible light, and UV light, and infrared light, and radio frequency, and X-rays, and so on. And from these equations, you can see that the higher the frequency, the more energy is associated with the radiation. And you can also see that the shorter the wavelength from this equation, because this is a constant, and that's what this constant, so the thing on top is a constant. So if lambda is very short, this becomes very big. So short wavelength light or high frequency light is associated with higher energy. Now the visible light the wavelength is about 400, 700 nanometers. A nanometer is 10 to the minus 9 meters. And for near UV, the wavelength is 200 to 400 nanometers. So these are arbitrary descriptions of various portions of the electromagnetic spectrum. Now, when you take a compound such as a conjugated diene, it absorbs, depending on the number of double bonds, either in the UV or in the visible region. If it absorbs in the visible region, you'll see it as a colored object. So if you buy a carrot at the Safeway store, it's orange because there are compounds in the carrot that have quite a lot of double bonds. Now, the UV spectrum does not consist of a series of sharp lines, but instead of a series of broad peaks. And what you will see in a typical UV spectrum maybe something like this. This might be 260 nanometers. This one is say 240. This one say 200. And this is the absorbers. If something absorbs strongly, you'll see the peak gets bigger. It's not a sharp signal, it's sort of broad. And the reason why it's broad is that these electronic transitions can come from different vibrational states, not from just one state. But we don't have to worry about that. All we need to know that this is called lambda max. So the more conjugated double bonds that you have, this spectrum is actually for this compound. The more conjugated double bonds that you have, lambda max moves to longer and longer wavelengths. And what is happening in the formation of the spectrum, or in the absorption of the radiation, is that an electron from the highest occupied orbital is being boosted up to the lowest unoccupied orbital. That's what's going on when a compound absorbs UV or visible light. Now I said that the more double bonds you have, the more the lambda max moves to longer wavelength. And in fact, butadiene has a lambda max of 217 nanometers, whereas a simple olefin has a lambda max like ethylene of 170. So you can see that putting even one double bond into conjugation makes quite a significant shift to the lambda max, the wavelength at which the absorption is the greatest. Now, if you eat a carrot, one of the things in a carrot is something called beta-carotene. And beta-carotene has 11 double bonds in conjugation. 11. And beta-carotene, as you would expect from what I told you, we have a Landemax that's moved this way quite a lot. And in point of fact, it absorbs, it has a Landemax of 497 nanometers. So when you shine this little light on it, it absorbs the 497 wavelength, and what gets into your eye are the other wavelengths. And the 497 wavelength is a bluish-green color, and that's absorbed by beta-carotene, and what you actually see is the complementary color, which is reddish-orange. So that's why, in a very rough way, why a carrot is that color. And if you took a compound that had only 10 double bonds in it instead of 11, the Landemax would shift a little bit to lower wavelengths, and the color would change. And ultimately, when you get to just this thing, the Landemax moves in a region we can't see. So it becomes colorless. So that's one of the ways in which organic compounds are colored. And as a result, we see certain things. Now, that's enough about the theory of conjugated systems. What I've done is I've told you that the conjugated system for which you can write a resonance structure. Let me just write a resonance structure for butadiene. Well, one of the things I can do is to do that. It's not a terribly important resonance structure because, remember, I gave you some rules the other day. And one of the rules was that if you separate charges, the resonance structure is less important than if you've got another resonance structure without separation of charges. But it's nonetheless a resonance structure. I told you today you can write resonance structures. It's more stable than if you couldn't. I've shown you how to draw or how to imagine the formation of molecular orbitals for butadiene, and I indicated to you that the case of butadiene, you start with 4 p orbitals, you end up with 4 molecular orbitals. These orbitals in the case of butadiene do not have the same energy. You've got 4 electrons to feed into them. You feed 2 into the lowest one, 2 into the next one, and then you've got 2 that are empty. And when you shine light on the stuff, if it absorbs the light, one of the electrons in the highest occupied molecular orbital is boosted to the lowest unoccupied molecular orbital. And if the gap between the highest occupied and the lowest unoccupied, the gap is small, the energy required is not very big. And if the gap is huge, the energy required is likewise big. You know, if you've got to throw a ball over a wall that's this high, it doesn't require much effort. But if the wall is sort of twice the size of the ceiling, you've got to really go. You need more energy. So if the gap between the homo and the bimbo is big, you need more energy, so you need a shorter wavelength. I've also told you today that butadiene can exist in different conformations. 2 of them are important, the so-called S-cis and the so-called S-trans. What I want to tell you now is something about the reactivity of conjugated systems, and I will deal mainly with the reactivity of butadiene. If you treat an alkene with an electrophile, one part of the electrophile acts to one end of the double bond, the other part acts to the other end. But if you've got a conjugated system, the situation is quite a bit more complicated. Supposing I take butadiene, this pen's useless, let's get rid of it. you get two products. You get mainly 78% that one and 22% that one, which is mainly E. Now what's going on here? Clearly, the hydrogen from the HCl is added to one end of the system, and the chlorine has added either to the adjacent carbon or to the carbon right the other end of the chain. And there's been a movement of the double bond. So this is a lot more complicated than if you add HCl to propene. Probably remember from last year that if you add HCl to propene, what you get is this first, and that then gives you that secondary chlorocompound. Okay, I can see some of you in the front can't see this. How low can I get? Can you see at this level? No? Can I see at this level? Thank God. These boards are basically only half as high. These are designed these things. They're going to be dumb. That's what happens with propene. Obviously something more complicated is happening here, and I need to explain to you what it is. So let me write it like this. That's the first thing that's happening. You can see I can write a resonance, two resonance structures for the species that's formed. And so chloride could attack there, or chloride could attack there. If it attacks in this one, what you get is that, and if it attacks here, what you get is that. So I can show you the way in which the products are formed. Because the products are formed by capture of a resonance stabilized allylic cation. I can move the pair of electrons here, and I can get that. Now this, obviously, could react also in that form. And if I do that, I will then get this, and I can write a resonance structure for that, which again will give me the terminal chloro compound, but now the double bond is Z. And remember, when I first wrote it up, I said it's mainly the E isomer. Clearly, you know that this is a less favoured conformation than that one. So the more favoured conformation reacts in this way to give you a resonance stabilized allylic cation. Because it's resonance stabilized, and there are two structures, you write a plus on two different carbons. And you can imagine the chloride ion attacking either of those positively charged carbons. So that accounts for the formation of the two products. But there are a few questions, there should be a few questions about that. Why isn't, for example, that I'm if that were to occur, first of all, I'd get a primary carbocation, and secondly, it would not be resonance stabilized. And remember, I told you, you can write resonance structures more stable than it would otherwise be. So this thing here is bad for two reasons. One, it's a primary carbocation, and primary carbocations are less stable than secondary, which is less stable than tertiary, and it's competing against a secondary carbocation, which obviously by itself is more favorable, and the secondary carbocation is resonance stabilized. So it's an absolute loser. That one. So it doesn't go that way. So now you know why the hydrogen is picked up at the terminus of the diene, and you know why you get chlorine in two different places, because the intermediate carbocation is resonance stabilized, you can write a couple of two different positions, and you've got some sort of idea why it is that the ether isomer of one of the products is the major isomer. Now, what you still don't know, because I haven't told you, is why is it that the 1,2 addition product, in other words, this one, 1,2 because we've added something, one carbon and on the adjacent carbon, whereas this is a 1,4, 1, 2, 3, 4. This 1,2 and 1,4 has got nothing to do with the naming of the compound. A 1,2 addition means addition on adjacent carbon. A 1,3 addition means addition on carbons that are related 1, 2, 3. And a 1,4 addition is carbons that are addition, one piece at one end comes the other end, and there are 4 carbons in between. What you don't know yet is why is it that, well, I haven't said very much about why it is that we get 2 compounds, the 1, 2 and the 1, 4, and also something I haven't yet told you. If you do the reaction at a low temperature, you get mainly the 1, 2, and if you do it at a high temperature, you get the 1, 4. And if you do the reaction at a low temperature and you heat up the mixture, the composition of the mixture changes as you increase the amount of 1, 4. So clearly there's something else that is going on here.